Good afternoon, everybody. Welcome back. We have the fourth and final session of the Motor Summit 2020. I have the pleasure to be your moderator for the last block. I'm happy to introduce you to Maarten van Werkhoven, our final speaker. He'll talk about the coordination and alignment of standards for energy-efficient electric motor-driven systems. We call that the CAISEMS project. Maarten is a director of TPA Advisors, residing in Amsterdam, Netherlands. He has a degree in mechanical engineering and business management. He works together with Rita Raleigh as operating agent of the IEA Technical Cooperation Program 4E, Electric Motor Systems Annex, the famous EMSA, and he is involved in several Dutch and international projects related to electric motor and systems efficiency. Lately also in the IEC world with the Advisory Commission of Energy Efficiency. Welcome, Maarten, you have the floor.
Good afternoon, everybody. Welcome to my presentation on the project called CAISEMS, Coordination and Alignment of IEC and ISO Standards for Energy-Efficient Electric Motor-Driven Systems. My name is Maarten van Werkhoven. I'm an independent consultant working from Amsterdam, the Netherlands, grades in mechanical engineering and business management, and expertise mainly in energy, technology, sustainability for industry with a direct link to research and policy. Active in different programs and projects, for instance, as operating agent within 4E EMSA. This is a technology collaboration program under IEA. Also member of the ACEE Advisory Committee on Energy Efficiency, and active in numerous projects on energy efficiency in industry and buildings. My presentation has a few sections from energy and electric motors towards motor and the system, on standards concerning those motors and system components, then the project CAISEMS itself, and a few conclusions. On energy and electric motors. Motor systems are good for more than half of the global electricity use. The main applications for motors are the pumps, the fans and the compressors for air and cooling. These three main applications are good for 75% of the total electricity use of electric motors. The other quarters being other systems applications like materials operations, milling, internal transport systems and other production machines. So I said overall more than half of the global electricity use is into motors and its different applications. In 2015 this was approximately 10,700 terawatt hours. And of that section, more than 2/3 is into industry. Now, moving to the electricity use per region, and again application, here we see a division of the global electricity use for 4 sections. 3 main economic regions being China, European Union and the United States of America, and the 4th being rest of the world. As you can see again the differentiation to the different driven applications, the pump, the fan and compressor and other systems. And what this also a bit tells us is how the other potential for energy efficiencies in driven applications. When you think of the current regulations in place for electric motors and motor-driven systems, in China we have the pumps, the fans, compressors regulations, minimum requirements on their efficiency. The European Union has a regulation in place for fan and pumps under revision currently, and the USA has now regulation in place for pumps only. And the rest of the world mainly minimum energy performance requirements for motors. So this says also something of the potential for extra savings in the world. Switching to the world market, the total turnover value in 2015 is approximately 100 billion American dollars. At the left we see the pie for the different regions again. 1/3 is into the rest of the world and the other 2/3 into the 3 main economic regions as mentioned. At the right we see the division of differentiation to the different components of a motor system, and there 1/4 is into the motors and the drives, 3/4 into the other 3 main driven applications, pumps, fans and compressors. Going from the motor to the system. I show you this slide with this figure. You may have seen this before, showing the different components of a motor-driven system, with in a heart the electric motor, at the right the driven equipment, in this case the pump, it can be a fan, compressor, and alongside sometimes a mechanical transmission, a coupling, a gearbox, a control being a starter, a speed drive, other type of control, and at the output side, following up with the pump, we have of course numerous valves, piping, etc. This together is the motor-driven system. Now, when we want to when we address efficiency of a motor-driven system, we address the combined efficiency of those different individual components. Into this slide, where I show you these different components and the efficiencies for, to start with, in orange, a standard system. For 37 output, we need in this case 100 input. Take some water. So the efficiencies of each component leads to an overall efficiency of the system by multiplying each individual efficiency by the other. Now, adding or switching the standard component for a more efficient component, we are able to increase the efficiency of the system to 65. So almost doubling the efficiency of the standard system. This is possible, for instance, in this case, by getting rid of some valves, instead of that adding a VSD, also getting rid of the transmission, so making a direct drive, adding a high efficient motor, a better high efficient driven application. So overall, almost doubling of the efficiency is possible. This graph shows you the losses in yellow for the standard system, losses per component, and in orange for the optimized system. Again, here you see, especially at the other system components, much lower losses due to getting rid of the valves, adding some losses by the VSD, but overall very much lower losses of the overall system. Moving to this slide, complexity of the EMDS, of the motor-driven system. Again, here the efficiency of the system is defined by output divided by input, so the black arrows. But when you want to know the efficiency of the individual components, different units are used. For instance, for the control, input is in volt, current and hertz. Output is in volt, current, hertz and total harmonic distortion. For the motor, that's the input, but the output is only in torque and speed. For the driven equipment, the output is then in pressure, flow, weight, force, or deceleration, acceleration. So when we want to design and install an efficient motor-driven system, it comes down to planning, assembly, testing and putting into operation. One has to take into account all these different efficiencies of the components. We have to know them in order to be able to at least calculate the overall efficiency. Of course, one can test the efficiency of the overall system, but it's only possible at the manufacturer side, not at the end user. I will come to that back later. So, a system optimization has many advantages, as listed here. The system can be lighter, smaller, cheaper. It leads to higher reliability of the system, less waste heat due to less losses, a lower peak load, and also, of course, lower electricity consumption and cost. Moving to the section standards. Again, the same system figure. Now, when it comes down to standards for these components, we have two main standardization bodies. At the left, we have the electrotechnical components, which are defined by the International Electrotechnical Commission, IEC. At the right, we have the mechanical components, which are defined by ISO, the International Standardization Organization. Each component has its own technical commission responsible for that specific component. When it comes down to standards, three main elements are important, being the scope, what is exactly the definition of that component, testing, how do we test the efficiency of the component, and classification, how do we rate the efficiency. Both IEC and ISO control the knowledge in industry with regard to these components. And as I mentioned, many different individual TCs are responsible for those individual components. But also, some of many TCs have a history, goes back a long way. But the TCs have also been working relatively separately, with relatively low cooperation. And that's one reason for initiating our project CAISEMS. Getting more specific, or especially on the item of, is the system bolted together at the factory or at the premises of the end user? Again, here this comes from an ISO standard, the FAN standard on system power losses, where the different components are defined and testing is possible from wire to air. Efficiency is also defined wire to air. This becomes much more complex when it comes down to an on-site assembly at the premises of the actual end user. At the manufacturer's place, it's possible to test, to calculate, what we call ex ante. At the industrial end user, it is much more difficult, if not impossible. One can work towards an acceptance test, but otherwise one needs to be able to calculate the efficiency of the overall system, so ex post. Brings me to the CAISEMS project. CAISEMS, it's about system standards. The project is initiated by the Advisory Committee on Energy Efficiency, which is a subcommittee just below the SMB, Standard Management Board from the IEC. It's about the coordination and alignment of specific standards for energy efficiency. Goals, overall, generic, to provide a platform to initiate and organize coordination and alignment activities between those DCs, and also initiate concrete cooperation between those DCs on the issue of energy efficiency. We started in September last year in Tokyo. 60 members, active, passive. Active means you actively participate in meetings. Passive means you get informed, you get the documents, and if you want to, you can comment. If not, that's fine. Tomorrow, the 20th November, we will have our fourth meeting. Some goals and benefits of this project. Goals, I mentioned some before. One is to give a sort of overview of the existing IEC ISO standards on energy efficiency, so this current status quo, so to say, what is currently available. Providing a platform for systems efficiency, so wire to water, wire to air. And work towards system calculation of efficiency, so from components to system, ex ante at the factory with the manufacturer, ex post with the end user. So system acceptance tests. And also making it possible to calculate the efficiency at any applicable operating point. Benefits, I think I would mention just one, also looking at the time. I would say one is to avoid duplication, unnecessary redundancy and conflicting elements in standards, leading to a interoperability for the different standards of those falling within the boundaries of the motor system. So main goal, I would say, main benefit is that these each ISO and ICTC made different metrics, but these all fit into a general combined applicability for system performance. Next steps for CAISEMS. At the moment we have a number of liaisons in cooperation with ICTCs and ISO-TCs. We have now produced two documents. One set is the background document, set of 5 documents on standards, terminology, metrics, operating points, and minimum energy performance requirements in place currently. The second main document is Work Plan Edition 2. This one we will discuss tomorrow in our meeting. And then coming period we will need to decide on the first work items for this joint activity by specific IC and ISO-TCs. Of course, in the meantime, ongoing activity will be building on a further involvement and planning cooperation between those stakeholders. My main takeaways for this afternoon. First of all, above everything is the the awareness that efficient electric motor systems can source substantially to the global climate goals. Then the role of internationally coordinated standards is large, because internationally coordinated standards will enable national governments to establish effective minimum energy requirements for efficient products and beyond, from product to system. It will also deliver efficiencies beyond the own individual scope of one component. Suppliers, end users, service industry will profit from that increased transparency and interoperability of the EMDS standards. And last but not least, for that we need the IEC and ISO standard committees, the TCs, to interact more closely and to deal with energy efficiency in motor-driven system in a timely fashion. 70 minutes, well, thank you for your attention, and I think now it's time for questions. Thank you.
Thank you, Maarten. Good presentation for a new project. Very complex issue, but your explanation was very clear. Thank you very much.
Thank you.
We got a lot of questions, which I will try to relay to you.
We have time enough?
Yeah, first question. First question is, why did ISO and IEC not better collaborate already 10 years ago?
Well, that is an interesting question, and I do not know if I'm the person to answer that. But one obvious answer, I think, is that every extra effort needs time. And what I see is that both from IC side and ISO side, the technical committees are very much into their own dedicated work to their own component product. So asking them to look over their own borders is something which takes extra time for them, and thus is not so obvious to start with.
Okay. We have another question which is a little bit related to that. Maarten, are you optimistic to bring the motor people on one side and the fan and pump guys at the same table?
Oh yes, very much I am. And I explain why. I think when we look at where we are now, and we is then overall every stakeholder involved, is, for instance, for the fan industry, they are very much on the right route. They are very active and have produced very sort of standard covering this wire to air efficiency. So and that can serve as a good example also for other motor-driven systems. At the same time, it takes a lot of time to get the different entities together, and especially to design together a route as where we want to go together. And that's something which is, of course, the more people you have at the table, maybe the more difficult it gets. But as a baseline, I am optimistic, yes.
Okay, good to hear your optimism. The next question is asking, does this concept of wire to air actually save energy?
Potentially, yes, it does. It, of course, depends very much on how the engineer applies this wire to air. We have heard today again from Mike Ivanovic and Jeff Lockwood on different metrics, different methods, but with the same goal is working towards energy efficient applications. So yes, in fact, when you apply it in the right way, it saves energy.
And here's a very challenging question. I don't know whether you are conceptually the person to answer. The question is, how can the regulator, say the European Commission, adapt to such a new wire-to-air concept?
Yes, well, it is an interesting question, also a difficult question. Depends a bit on how you look into the definition of the system, which is a very complicated question. But for instance, in Europe, we have the eco-design, which is from origin product-based. But as we now see, when you want to make real steps towards energy saving, you need to broaden the scope, broaden the definition of the system. And with this wire-to-air definition, it is possible for regulators to save energy, to apply this metric and to apply this definition into their regulations.
Mm-hmm.
Yeah.
So far, you have talked about this CAISEMS concept in regard to pumps and fans and compressor. I have a question. Will you also have a look to the electrical machines they will be used in electrical cars?
It is that would be a challenge, I would say, because it's again a different application, but at the same time, getting to the roots, to the base goal of CAISEMS, that could be possible. But it's not on the planning for next year.
Okay, it's not the short range, but the longer range. And now I have a difficult question. I have to read it, how it comes in. Obvious, the focus on the transmission and application for there are potentially the highest gains possible. Combined efficiency of transmission application is something like 66%. Here comes the question. How do you explain the constant focus on improving the efficiency of the motor? Where does this bias come from? He's not happy that he feels we are always talking about motors, motor efficiency, and not about the application efficiency and transmission.
Well, I think it has something to do with historics, where the motor was the first product which came into with this efficiency classification, IE1 words. That's maybe one reason. Another one is that I wouldn't say it is bias. In the end, when we talk about, for instance, CAISEMS is about the motor system, and we for sure want to include all the different components and take into account the different efficiencies of those components. And where it was relatively maybe now looking backwards easy to define the efficiency of the motor, it becomes more complicated for other components. For transmissions, there is no efficiency classification yet available. For pumps and fans, it's much more complicated, differentiated, so that's more difficult. But the bottom line is that we would like to address all components overall as one system efficiency.
Okay, thank you, Maarten. Thank you for your explanation. Thank you for your excellent presentation. I wish you luck with your project. I'm sure it is a long-range project. It's not going to be finished by the end of this year, but maybe take some longer. But you have a valuable contribution to saving energy and improving this systems approach. Thank you very much.
Thank you.
Bye-bye.
Thank you. It was a pleasure.